All right, so any of you who are interested in things like JPL or NASA or SpaceX or places that get away from the Earth, next topic is escape velocity. And of course, if you're going to send something to another planet or another solar system, which granted we haven't and probably won't do in our lifetimes, but if you were to do such a thing, you are going to have to reach escape velocity. So we're going to talk about how do you figure out how fast you'd need to travel in order to escape from some particular astronomical body. And it turns out the way we need to think about this is through energy conservation. So as a reminder, energy conservation in its most basic form says that the change in energy is equal to 0. And in that case, we'd be able to say the potential energy of gravity initial plus the kinetic energy initial would be equal to the potential energy of gravity final plus the kinetic energy final. Now, finding the escape velocity is actually going to come through the kinetic energy initial. We already know how to write what gravitational potential energy would look like at every point. So again, you'd be thinking about u is a negative integral from infinity to r of minus g m1 m2, or big M small m, r squared dr, which will eventually give you, with a little bit of work, minus g, the two masses, over r. All right, so really we need to think about, presuming the initial condition is where we start and how fast we have to be moving to escape, what would the final potential and kinetic energies look like? Well, we need to think about what does it mean to escape. So let's say we have a body like the Earth, and I'm going to do something that may surprise you. Let's say that we have an object that's actually already in orbit around the Earth at some particular radius. I want to rewrite that v. How fast would that v need to be in order to escape? Well, to escape means we're going to have to take this object, and I'm not liking where I put it. I'm going to put it down here, going this way instead. How fast would that object have to be moving so that our mass out here ends up traveling off and reaches infinitely far away? Now, why infinite? Because infinite's the only place where the gravitational force goes to 0. So gravitational force goes to 0 only as r goes towards infinity. All right, now there's another trick to it, and that is once we've escaped, we've gone to infinity, our speed will go to 0. We want to just barely escape. We want to find that minimum condition that we just barely make it to infinity. We could, of course, go faster, and if you do, you still escape, but you escape with prejudice. You reach infinity and you've still got a velocity, and you're going to still keep on cruising to even greater infinities. Okay, yeah, I know the idea of greater infinities is weird, but ask a mathematician. There actually are different ways of thinking about infinity. So we're not going to get into any of that. We're just kind of concerned with what is the limit that we just barely make it out all the way to infinity. So this should be telling you something. First, the gravitational energy final should also go to 0 because we're dividing by infinity. And the kinetic energy final is also going towards 0. So now we can make a statement. Minus g m, big mass, small mass, over our initial radius, plus 1/2 the mass of our spacecraft, or whatever we're sending away, times v squared, and this will be our v escape, must be equal to 0 plus 0. So now it's super easy. We move things to opposite sides, we cancel stuff out, and that pretty much gives it to us. So, it'll be plus big G, big M, little m over r, initial, wherever we're starting. We'll cancel out the m. We're going to have to multiply through by a 2 and take the square root. And I am going to both multiply by 2 and take the square root at once, which is a little risky, but I think you'll follow the 2 algebra steps. So this is escape velocity. Now notice, I very deliberately didn't draw this on the surface of the Earth. I could have. We could have started with the object right here. What velocity would it have to escape from the surface of the Earth? And if you do that and you put in the radius of the Earth, you'll of course get this escape velocity from the surface of the Earth, assuming it had no atmosphere. And everything is good. You still get out to infinity. Or you can start from an orbit around Earth and ask, okay, well, starting from this orbit, how fast do I have to be going? Why is that interesting? Well, think about this. If you want to escape from the solar system, you're trying to escape from primarily the sun. But we don't start from the surface of the sun. It's not like you set your rocket on the surface of the sun and then go, okay, I'm going to launch it off the surface of the sun and escape. No, we actually start from Earth orbit, basically. So the Earth's going around and we launch our rocket off the surface of the Earth. And we need to know how fast does it need to be going relative to the sun in order to get away and escape from the solar system. And in that case, you'd put in the mass of the sun and you'd put in the 1 AU, the distance the Earth is orbiting away from the sun. And you would use that to figure out, how fast you'd need to go to escape from the solar system. Interestingly enough, there are a handful of objects that have achieved escape velocity from the solar system. Some of the Pioneer spacecraft, at least from the US, and the Voyagers. There are probably other spacecraft launched by the Soviet Union. There may even be others. I'm not really aware of any Chinese spacecraft that's been explicitly launched to escape, but it wouldn't be too surprising to find out there is such a thing. If any of you happen to know, I'd love to hear it. All right, so this is escape velocity. It can be used from any position relative to your big central mass. And next up, we're going to do a quick example with this, and it is going to be the very basic one, escape from the Earth.